Now if you look at this whole thing, then it tells you the difference between DC and AC. In the lower circuit on the left side, you see that a resistor is connected to a battery, so the current will always go clockwise. If you look at the right side, then there is some device which is able to generate square wave. Square wave means the voltage will vary from say +5, -5, +5, -5, +5, -5 volt like this. It will remain +5 for some time, -5 for some time, +5 for some time, -5 for some time, and so on. Resistor will obstruct this current and will make it E by R, and whatever is the direction, plus on the left or plus on the right, current will flow accordingly. So current can be clockwise for some time till the time voltage is plus here, and it will be anti-clockwise for some time till the voltage is plus here. So if you look at the graph now, you can understand that here in the left side, current is positive and remains positive, and on the right side, current is positive for some time, negative for some time, positive for some time, negative for some time. It depends on the voltage. If voltage is positive for some time, in the same time current is positive, and if voltage is negative for some time, current is negative for that time. So when current changes its direction, we call it alternating current, and if current does not change direction, we call it a direct current. Direct current is what we have been dealing most of the times. However, when we were discussing LC circuit, that time you saw how current was changing its direction. In these examples, I have shown the magnitude flat. Look at this right side graph. I have shown it flat. It doesn't have to be flat. We have been talking about AC as current which changes direction. It can also change magnitude. So in fact, in reality, the current that we use is not flat, but it is variable. It is like sine wave. So if you look at this graph, then current is positive for some time, negative for some time, positive for some time, negative for some time. It is alternating current. But it also has one more thing. Its magnitude is changing as well. It is 0, then it rises, 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 attains its maximum value, then it falls, 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 becomes 0. After this point, it changes its direction. Then it rises in magnitude in the opposite direction, attains maximum value in magnitude at this point, and then the story keeps on repeating itself. So the batteries that you see which are available in the market, which provide power based on the chemical reactions, they are responsible for DC. But what you get in your sockets available in homes, offices, etc., that's not it's not DC that you get there. Their voltage continuously fluctuates, and because voltage fluctuates, current also has to fluctuate. So one wonders how to get this type of voltage which continuously fluctuates. First of all, why get this type of voltage at all? You know that we can get voltage if in magnetic field some conductor is moved or magnetic field is changed and conductor is present, so on and so forth, if you change flux. A very convenient way to change flux is to make something rotate. When something rotates in its own place, it does not have to go further. It just keeps on rotating in its own place. That is a very easy way to generate electricity. And when something rotates in its own place without going from point A to point B, if you see center of mass over a period of time, then you get this type of voltage which is sinusoidal or cosinusoidal in its behavior. So because the voltage source is providing sinusoidal behavior, current can also be sinusoidal or cosinusoidal. So first we discuss how can we get a voltage source which is able to provide voltage of this pattern, sine wave pattern, whose not only direction that changes, but also magnitude changes. Consider some coil. It has several turns, say n turns, rotating in magnetic field which is created by some permanent magnet or by some electromagnet. The magnetic field is from north to south, so its direction is like this. The axis of the coil is this, and one end of the coil is connected to a metal ring. Other end of the coil is also connected to a metal ring. So this is welded, connected strongly with this ring. So as the coil turns, the rings are also going to turn along with the coil. You see, when you are trying to generate electricity from something rotating, then the challenge is that how do you connect to something which is rotating? And that problem is overcome by using carbon brushes. These two which you see here, these are carbon brushes. So as ring rotates, as the coil rotates, rings rotate, both the rings rotate, and when the rings rotate, brushes always maintain the contact. So you can think of it like this, that this is a zoomed version of a ring. If something is rotating like this, there is something like this here, which always is in physical contact with this ring. This thing is always in physical contact with the ring, and it is carbon brush. So one here and one here. Carbon brush is not rotating. It is rubbing at this point of contact. So rubbing takes place at this point of contact, and you are going to connect your external circuit from these 2 points. So external wire connects this carbon brush, external wire connects this carbon brush. You connect whatever you want across these 2 fixed brushes. Brushes are fixed, and that thing will get electricity. How will it get electricity? When the coil turns, then its area vector makes different angle with the magnetic field. So if the magnitude of field is constant, magnitude of area vector is constant, even then the direction is changing. If you consider area vector to be in one direction, up or down, then you can clearly see that as it turns, the direction of area vector changes. It is the direction of area vector that is the key. So as that changes, the flux changes. And coil does not like change in flux. So it opposes change in flux. So there is an induced EMF across these 2 points. So the same 2 points are connected to your house wiring also. Okay, there may be so many complications, but for the sake of simplicity, so there is voltage, potential difference across these 2 points. Even if you don't press the switch on, there is potential difference. The moment you press the switch on, whatever device is connected, current starts flowing through that. We can do mathematical calculation to find out the induced EMF in such case, and we can prove that it is sinusoidal or cosinusoidal. The discussion can start at any point when area vector is making any angle with magnetic field. But for the sake of simplicity, let us say that initially area vector makes no angle with B. That is, at t equal to 0, we are supposing, it doesn't have to be the case always, if at t equal to 0, area vector is parallel to magnetic field, then what is the flux? Somebody can take some other reference point t equal to 0 if area vector is perpendicular to B or making any angle. So that is entirely our choice. Now let me take t equal to 0 when area vector is parallel to magnetic field. So it is not what is shown in this figure. In this figure, what is shown is this type of situation. So let me rub it off. So imagine that the plane of the coil is perpendicular to B. Plane of the coil is perpendicular to B. What you see in this figure, imagine it has turned by 90 degrees, and you can visualize the situation then. It will look vertical. So turn it by 90 degrees, and that is what we are calling as t equal to 0, and flux is maximum at that instant. But just saying flux is maximum doesn't guarantee EMF to be maximum, because EMF has to do with rate of change of flux. How quickly flux is changing, that will decide the magnitude of EMF, not just the value of the flux. In time t, the coil will turn by how many radians in time t? Omega t, coil is going to turn. But then area vector will also turn by the same angle. So after time t, area vector makes how much angle with B? After time t, area vector will also turn by omega t radians. Earlier it was making 0 radian angle. Now it will make omega t radian angle. So now flux will be BA cos theta, where theta is the angle between area vector and the field vector, and that angle is omega t. I hope this logic is clear. If coil turns by theta angle, then area vector also, its normal also travels by theta. Both travel by theta. And earlier normal was making 0 angle with B. Now it will make omega t angle with B. So phi as a function of t is given by BA cos omega t, and E induced is minus d phi by dt, which is BA omega sin omega t. But then we should also write number of turns. So BA, BAN, BAN, BAN. So N will come everywhere. This is the result assuming at t equal to 0, the flux is BA. BA for one turn. Now look at this result. N is fixed, A is fixed, B is fixed. It is all about angle, and angle has to do with rotation. When time changes, angle changes, and you have induced EMF. And this is a sinusoidal EMF. Yes, omega is also here. This is a sinusoidal EMF, so it will become 0 sometime, it will become maximum sometime, again 0, it will repeat continuously. And if you have resistance, it will just follow what EMF says. If EMF is maximum, resistance will make current maximum. If EMF is 0, current will also be 0, provided it is resistance. If you have inductor will just not follow EMF, because inductor opposes change, and here EMF is changing. Resistor can only apply brake on the magnitude of current. So just imagine a simple concept that if you change flux, there will be induced EMF. That simple concept or observation, experimental observation, is powering the whole world. How come so much of electricity is generated? The key idea is the same what we discussed. What was shown to you was some magnetic field created by either permanent magnet or electromagnet. Then in that field there was a coil, and then some mechanism was used so that you can connect something to the ends of that coil. Even though that coil is turning, still you can connect. Some mechanism is devised to handle that situation. That was just a rough type of thing. Now, engineering makes things better and better and better. So generally you use coil along with something soft iron type of thing. You actually wind the coil around that soft iron core. The reason is that it helps in increasing the magnetic field because core itself gets magnetized. Moreover, you don't have to use just one magnet. You must have heard of three-phase. So one can use different types of fields and one can get three-phase electricity. There are many such finer points that we don't need to go into at this stage. But if you want to do this in large scale, then of course you need something big in terms of coil. So if it is big, then you need something powerful to turn it. You have to turn it. You can turn it with your hand also. So you just turn it with your hand and you get you can make small things work also without any problem. Bulb will glow as you turn your hand, so that will work. But if you want to power the whole city, then you need something really powerful. And turning the coil is achieved by passing steam, and steam hits the rotor or turbine, and this turbine is connected to this coil. So turbine is turned by steam. Turbine is turned by falling water from some height, like some places where water is, resources of water are good, like hill areas where water falls from height. In those areas, one can set up a power plant in which water falls and hits the blades of turbine. Turbine rotates, and that turbine is coupled to this coil, and that coil turns, and there is magnetic field, of course. If you don't have water resources in that place, you can use steam, and steam will hit the blades of turbine. Turbine will turn, and to get steam, you can use coal. In fact, coal is the most used source in our country for producing electricity. So a lot of coal is burnt just to produce steam from water, and you can use nuclear power. So nuclear power can be used to heat water so much that it gets converted to steam, and then hit the blades with steam. Blades will turn, and as turbine turns, the coil is connected to turbine, and the coil turns. When coil is wound around the soft iron core, the whole thing, the coil wound over the core, is called armature. There is no need to it is not necessary that you wind the coil around the iron core for this concept to work. It will work even without that, but you want to make things more and more and more efficient, and you realize that soft iron core works better because it magnetizes. So with the soft iron core, the combination of the coil is called armature. Armature is coupled with turbine. Turbine has blades. You hit the blades by some mechanism, make the turbine to turn, and as turbine turns, the armature turns, and as armature turns, coil is turning, and as coil turns in magnetic field, you have induced EMF. You can take current from it. Somebody would be taking current from it. There are so many people connected to it. So it is always there. Some current is always going to be there. And of course, there are other ways to turn the turbine, like wind. Wind can turn the turbine. These are the unconventional resources, but they are becoming more and more important these days. So this is in large scale. The same thing can be done in small scale also. So like before inverters became popular, people used to use gensets in homes and offices, shops, etc. And still many people use them. So inverters work completely differently. Inverter discussion doesn't fall in the diagram which we discussed. It's a completely different device. When we talk of gensets, then you have to turn the armature somehow. So there you turn it by using some chemical power, chemical energy. Chemical energy is stored within petrol. Chemical energy is stored within diesel or kerosene. Kerosene, diesel will be cheaper. So this is how generator turns armature. And when armature is turning, there is magnetic field inside it, and you get the induced EMF between 2 points. So you take those 2 points, connect any socket of your home to those 2 points, and every socket, because it's in parallel, every socket gets that much of potential difference or voltage. So this very concept about rotation is driving the world, and it used to drive many homes, offices, etc. some days ago before inverters became so popular. If you recall the topic on gaseous state, then a term was defined called root mean square velocity. Here in this topic, root mean square voltage and current are going to be the focus for us. What you hear as 220 volt is actually not the peak of sine function. What you hear as 220 volts is not E naught. It is actually less than E naught. It is the root mean square voltage. The maximum voltage that we get in our country is much higher than 220 volt. Does anyone know how much maximum voltage do you get? Well, the answer is 311 volts. That's what we get, the maximum. In different countries, it is different. But broadly speaking, it is 110 and 220 volt. So if it is 220, maximum will be 311. If it is 110 in some country, then in that country the maximum voltage will be around 156 volts. What is the need to talk about root mean square voltage? Why not just talk about the maximum voltage? We are now going to discuss that point. Since current and voltage both are sine or cos functions, the discussion is going to be common. When we talk of a general current, then a general current is I naught sine omega t plus some constant that depends on your initial state. When you're pressing stop clock t equal to 0, it depends on that. I think phi, can it create confusion in this topic? Phi is flux. Okay, let me use delta. So delta depends on the initial situation. When you're pressing T stop clock, that time what is current? Let us find out the average value of current. You know from definite integration how to find average of a function. Function dt upon dt, limit will go from 0 to that point of time in which you want to take the average. Let us talk about this average for the time period, capital T, where T is given by 2 pi by omega. What is omega? We discussed it. The angular velocity of the coil which is turning. That was omega when we got the result equal to E naught sine omega t. But you can just say that if I is I naught sine omega t plus delta, then I is denoted graphically in this manner. And t is this distance from, okay, in time, it is this distance in time from here to here. Or you can say from here to here, whatever suits you. Or you can say from here to here to here, this is t, this is I. So here to here, or here to here, or here to here, they're all same. This integral here will be simply be equal to t. I naught is the maximum current. It is a constant, comes out of the integral. And when you have omega times capital T, this is just 2 pi. And cos of 2 pi plus delta is cos delta. So it is 0. So current is continuously flowing, and you know sine function, it is non-zero most of the times. It is non-zero most of the times, and we get the mean value for one time period 0. And if you observe for a long interval of time, then mathematically speaking, any long number can be divisible by capital T. The fractional part will be very, very small. So for any long period of time also, you are going to get the average current 0. But if this type of current flows for a long period of time, then the truth is that it is not 0 for most of the times. And if you allow this current to pass through resistor, it will dissipate energy every instant of time. Resistance does not care whether the direction of current changes or not. So just looking at the average value of current does not really tell us the thing going on behind the scene. So we need something else. How about trying with root mean square and see if we get something meaningful? There is another way to understand why the average current becomes 0 for a long period of time. Suppose this is not just capital T, it is some other time but which is massive. So what will happen if you put that T here? Look at this, look at this. Up to this step it is okay, but in place of capital T, it is some other T. In place of capital T, it is some other T. It is that T for long period. Let me call it T dash. So let me just change the discussion for a long period as 0 to T dash, 0 to T dash, 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 dash. Now this won't become delta, so I'm erasing this last step. Concentrate on this particular step. T dash is massive, but no matter how massive you make the angle, you just can't make cos massive. Cos is a bounded function. It will have to lie between -1 and 1. So the numerator, which is the difference of two cosines, will not become massive really. But denominator on the other hand will become massive because of T dash. So for a long period of time, as T dash becomes huge, I average also approaches 0. That's other way to look at this. So I was talking about how about trying out root mean square and seeing if it gives us something useful. First we are going to find average of square of a function. Consider I square function now. Now you know what is average of any function. Now the function is I square, not I. So average of this function would be, I'm talking of one time interval, 0 to t, that function dt upon 0 to t dt. Taking the constant out, now here omega t is 2 pi. Now this is good. These two vanish. And then capital T will also go. So after cancelling, let me write the final thing at the top. So this is mean square. Mean of square, right? And this becomes root of mean square. This is called RMS current and is denoted by this. So IRMS is I naught by root 2. We considered I as I naught sine omega t plus phi. When you have any such function, sinusoidal function, then the same logic, same discussion is going to work. So if you have some voltage like this, for example, now in the discussion where I had drawn the diagram, the voltage was E naught sine omega t, but that was obtained by considering t equal to 0 as the situation when flux is BA. So it depends what is your initial point, and generalization for voltage will also involve some phase constant here. So V is V naught sine omega t plus delta is a general result. I equal to I naught sine omega t plus delta is a general result. and it is not so that if V is V naught sine omega t plus delta, then I will be I naught sine omega t plus delta only. That's not necessary. It is not necessary that if time period for this is capital T, then time period for this will also be capital T. It is not necessary that if this is omega, this is also omega. But as long as it is a resistive circuit, now I'm talking about resistive circuit, then it is going to be same. And as long as it is about capacitor, inductor, etc., as far as our scope of discussion is concerned, if this is omega, this will also be omega. This is T, this will also be T. If this is sine, is it necessary this will be sine? No, not so. Even within our scope of discussion, if this is sine, then that also has to be sine is also not necessary. Inductor opposes change, so sine can become cos. Capacitor also has behavior due to which sine does not have to be sine. But I'm talking of resistive circuit right now, just resistor. Resistor can apply just break in magnitude, that's it. Resistor cannot change angle. Resistor just follows the voltage. If voltage says maximum, resistor says current is maximum. If voltage says I am low, resistor says okay, current is also low. Resistor just follows Ohm's law, V equal to IR. So if this Ohm's law is instantaneous law, by the way. Earlier when we discussed Ohm's law, that time it did not make sense really to say that it is an instantaneous law. We were discussing DC. But Ohm's law is an instantaneous law. So when we say V equal to IR, V instantaneous equal to I instantaneous times R. So resistor is the poor fellow. It just has to obey what voltage dictates. If voltage is maximum, V by R will be current. Maximum. If voltage is minimum, V by R will be current minimum. So resistor can only put a brake. It cannot change the angle. It cannot pull or push the charges. It cannot pull or push the charges like capacitor or inductors can do. It can just apply brakes. But pushing, pulling, a resistor cannot do, which capacitors and inductors can do. So if voltage is following sine pattern, then current will just follow sine pattern. Its magnitude will be decided by the resistor. So the point was that does it make some sense to us? Is it a useful thing for us? That was a point we were discussing. So consider some resistor in which this current is flowing and this much voltage is there across it. How much heat is generated in one time period? How much heat is generated in one time period in that resistor in which this current is flowing, this much voltage is applied? Answer is I square R dt. By the way, there is a simple way to understand this sine behavior also. If current is this, just apply Ohm's law. Instantaneous voltage will be how much? Instantaneous current into R. So I naught sine omega t plus delta times R. That is I naught R into sine omega t plus delta. I think this should be a proof that you can understand more easily. Just look at the pattern, sine rule, sine rule. This is V naught. So this proves that if in resistor current is I naught sine omega t plus delta, then voltage will also follow the same sign. It will not become cos or something else. And for this discussion, I think we won't even need the voltage, by the way. So this is 0 to t, then I naught square sine square omega t plus delta r dt. Please find this integral and see how much you get. In fact, we don't even have to calculate the integral. We had something similar for RMS discussion. Taking capital R out, 0 to t. Let me multiply by t, divide by t, I naught square sine square omega t plus delta dt. This t I can write as integral 0 to t dt. Does this strike you something? Is it not IRMS square? IRMS square? We discussed an AC circuit in which current I naught sine omega t plus delta was flowing through just resistor R. In one time period, the energy that will be eaten by the resistor is found to be I square RMS or capital T. Now this is useful. If you take the same resistor and pass a DC current of magnitude IRMS for the same time t, will not you get the same energy as heat? To repeat, take the same resistor, connect a DC source so that the current is equal to IRMS in magnitude, DC current now. When you pass it for time capital T, you will get exactly the same heat. That means a resistor does not know the difference between DC and AC, provided in DC the current passed is not I naught, but current passed is IRMS. It is not the mean current. Mean current is simply out of question. Resistor is going to eat energy every instant and average current is 0. So average current is simply out. It is not I naught, it is IRMS. So IRMS has great significance for us. And IRMS is given by I naught by under root 2. So with this we stop now and we continue in the next class.